tape. So the tape is rolling now. So we're officially started class. We've still got people logging in, which is fine. All I've got showing here is the is the current assignments as usual. Now there was one that was due this evening. Remember, I told you this one's a little bit lengthy, right? So I postponed it just one day until tomorrow. I don't want to wait. I don't want to postpone it too much though, because we want to keep a steady pace on our homework, so we're not too backed up when we get to the first test, which is, remember, that's scheduled for February the 25th. And I think that we're sort of on schedule. So I think we can make it by February 25th through the material that I want to make it through before the first test. So that's why I want to keep the due dates, kind of, again, pretty frequent here on a pretty regular schedule. Remember, though, as always, right, if you run past the due date the next day, at least you can request an automatic extension, right? So, but you have to do that within a day. So if you know you're going to continue working on a homework, or you just completely forget about a homework or something, make sure that by the next day you do the automatic extension request, so that you can have more time to work on the homework and still get points for that, right? So there's a slight penalty for running past the due date, but some points would be better than none. And then I posted a new homework on measuring change, right? So I've got that one due as Saturday. I'm hoping we'll get pretty far into that, but we'll see on Thursday where we're at with that homework. This one also is got more problems on it, right? Now, so it's kind of a little bit lengthier than some of the early homework. So again, you've got to stay working on your homework on a pretty consistent basis, right? To keep up with things. Now, that's even more important since we're within, a couple of weeks of the test. And I wanted to show you that I'm going to go to the class Blackboard page. So this morning I posted, so if you go to the class Blackboard page and to where it says sample test, here is the link to the first sample test. So this is a sample test, right, for you to use to prepare for test number 1. So of course your homework, and the lecture notes, right, et cetera, right, are preparing you for test number 1. But the sample test is also going to be really important to prepare you for test number 1. So before you take the first test, it's important that you open the sample test and that you work on the sample test. Now, some of the sample test you're ready to work on, but some of it we still have yet to cover. But you can start and then work on the problems that you can see and they're familiar to you, that we've discussed. The reason the sample test is, although the problems look a lot like the homework problems, they're not completely identical to the homework problems. So that's one of the reasons it's real important to work on the sample test. And another reason is, remember, I told you that the test questions are in many cases are not going to be sort of computational or algebraically focused questions, where it's just a matter of grinding through some algebraic manipulations or some computations and then coming up with a single number or expression as the answer. Sometimes the questions are going to be a little bit more conceptual, and that's because I want to make sure that you're not just using your calculator or some website, right, to help you do the computations and get the answers. So there are questions on here that you're not going to be able to, you're going to have to do them yourself. You're not going to be able to answer these, from using your calculator. All right. So that being the case, it's important that you look at the sample test, and so you'll understand the types of questions that you're going to be asked for the test. So this is really good preparation for test number 1. Really good preparation for test number 1, right? So I really strongly encourage you, as we're moving toward test number 1, right, that you start working on the sample test. Now, when you open it, you're going to think, my God, this is too long. This is a sample test. So it's longer than the test is going to be, okay? All right, because I want to give you plenty of chances to practice the different types of problems that we're doing here before the test. So don't get dismayed by the length of the sample test and think, the test is going to be that same length. No, this is longer than the test, right? Okay. And it's not a duplicate of the first test. So don't think that I'm going to ask verbatim the same questions on the sample test as I have on the test, right? Okay. This is preparation for the test, but this is not a preview of the test. All right. So all of that, I wrote a little disclaimer here below the test, just to, kind of a legal disclaimer here, what I just explained to you, right? That this is longer than the test, and this is not a preview of the test. This is preparation for the test, right? And of course, you've also got to do your homework and come to class and the other sorts of things you need to do, right, in order to be prepared for the test. All right. So now, so every semester that I teach, I use sample tests every semester. And every semester that I teach, after the first test, someone will, or many people will come to me and say, "Wow, I wish I'd looked at the sample test," right? So, because I knew the material, but the sample test would have really helped me prepare for the test. So you do not want to be in that situation, okay? So, so don't make that mistake of regretting not looking at the sample test. Okay, I promise you won't make the same mistake twice on the second test. If you didn't look on the sample test for the first test, you'll definitely look at it for the second test. So, but that'll cost you points. So just avoid that mistake, right? So go ahead and use the sample test for preparation for the test. So it is kind of lengthy, so it will take some time in addition to the homework. So that's what I'm saying. We've got plenty to keep us busy here, moving into the first test. All right, so there's my little spiel for the importance of sample tests. Do y'all have any questions
Professor can
right
you
now?
hear me?
Yes, Madison.
Oh, okay. Yeah. I was wondering if it'd be okay for me to go ahead and go over the sample test
Yes.
during my exam
Yes.
review.
Yeah, sure. Right.
Mm-hmm.
Yeah, that's fine. Yeah.
Okay.
So,
Mm-hmm.
right. So, or before the exam review, you can go over it at any point. Now,
Mm-hmm.
again, there's a mixture. The problems are kind of mixed up in things that we have already. I don't have them in a chronological sequence. So,
Mm-hmm.
so there are things that we've already talked about and some things that we haven't talked about yet. So when you're
Mm-hmm.
looking at sample tests, you're gonna have to kind of pick and choose as you
Yeah.
work through it. Oh, I know how to do this, but I don't recall
Mm-hmm.
that. So, and
Mm-hmm.
then save that for later. But we will get to all of the things that are on the sample test before the test, I think, in plenty of time. If we don't, then we'll leave it off the test. Okay. So you won't be
Mm-hmm.
tested on anything we haven't talked about in class, obviously. All right. So yes,
Okay.
so for everyone, you can start working on it, and you can bring the questions to Madison at any time about the sample test. Okay. One other thing I wanted to mention really quickly here is, because we're online, right? We have to take the test remotely. So that means that I want to just give you a little bit of instructions just to show you now, so you can start thinking about this of how we're going to submit tests, right? So I will post the test on the test day, and then you will write your answers on paper. You can either print the test paper and write it on there, or you can write your answers on a separate sheet of paper. It doesn't have to be on the test paper, although it's really convenient to do it on the test paper. But technically, it doesn't have to be on the test paper. And then you will scan that and email that back to me, right? And then I'm going to grade the scan thing that you send back to me, right? The scanned paper that you send back to me. It has to be in PDF format, though. You cannot take a picture of it and send it back, all right? Because I cannot easily manipulate pictures that you send back to me. So it has to be in PDF format. And that being the case, here's some instructions for how to scan in PDF format and how to then, well, of course, I think you know how to email that back to me, but how to scan, right? And then submit the tests back to me. So you can look at these instructions. I would start looking at them now, and if you want to, you can practice. Of course, you can scan into PDF with your phone, so it's kind of like taking a picture with your phone. You don't have to use your phone. You can use other devices for scanning, right? But it does have to be put into PDF form. That's really important because otherwise I cannot grade it. So here are the instructions for doing that. So if you're having, if you practice with that beforehand and you're having trouble doing that, then ask me about that, okay? Before we get to the test. So there are plenty of apps you can use to scan on your phone and convert to PDF, and a couple of them are mentioned there in this document, how to scan and submit tests. So that's under the test and answers section here, folder on the Blackboard page. Trust me, this is easy. This is not a complicated process, but just you might want to try it before you have to turn in the test. If you haven't done this a lot, which maybe you have, but if you haven't done it a lot, then you may want to practice it before you have to turn the test, so you know you're not, you don't have 5 minutes left before you have to scan and submit your test, right? When the test is due. Okay, you'll have plenty of time to take the test, however. All right, so that's just a little heads up, a little preview of coming events. Y'all have questions at this point? Do you want to ask? I didn't, so I'm moving on here. I didn't, let's see, I didn't pick out any homework problems to go over today. But if you have any homework questions, ask me that. Yoselin, you had, is Yoselin here?
Yes, I'm right here, sir.
Yeah, you sent me a question and you were asking me to go over it in class. Do we still want to look at that? I think that was from a past assignment though.
Oh, that was from, yeah, one of the earlier assignments.
Yeah, I think it was on.
I think I ended up figuring it out after I sent that because I went back to try to calculate it.
Oh, you did figure it out? Okay.
Yes,
All right. So we'll skip that one then. Any other questions that?
Yeah, I had
yes.
question with either 15 or 16 on just how to put the answers.
In which one, Mohammed?
Either 15 or 16, either one. They're both the same.
But which homework assignment?
On 3. Yes, this one right
this
here.
One? Okay, yep. All right, so let's open that and see. When you say just put in the answer, it wasn't taking your answer, or you were just wondering about the format?
Yeah, yes, exactly. I was just wondering like how to put,
well, let's read it. So it says the graph of this, apparently this is a polynomial function. Polynomial means function that means that the formula for the function just involves powers of x. So you would have things like x to the 4th power, maybe x cubed, x squared. Powers of x is how the formula for the function is composed, okay? And so it says state the intervals on which f is increasing and where it's decreasing, okay? And then there is a little instruction there on the side, and it says enter your answers in interval notation. Is that what's confusing you there, Mohammed? So
yeah, I see it. It's just I was a little confused on the increasing and the decreasing part, like how it is increasing and how it is a little confused, not too much though.
Okay, so actually we're going to have a poll question on that coming up here really quickly. So I'm going to ask almost this exact same question again. So remember, increasing means as you're moving left to right on the x-axis. So we're always thinking of the x coordinates as increasing, right? Okay, so those are always increasing. And then increasing or decreasing refers to what the y coordinates are doing as we're moving left to right on the x-axis, Mohammed. So we're always thinking ourselves as moving left to right on the x-axis. So notice as you're starting here along the x-axis all the way out here at minus infinity, right, and moving to the right, correct?
Right.
Then at first, the y values are going down, right? So that portion of the function is decreasing. But then when we get about right here, correct, right at that point, then the y values begin increasing, right? The y coordinates are increasing.
Yes.
So that part of the function is increasing. And then maybe about right here, it's hard to read that though. It starts
Yeah,
to,
I think I messed up with the numbers. I put in 10 and 5, I guess, which is supposed
you
to be
mean minus
4
5?
right now. Maybe.
So, yeah, so you may be off a little bit there.
Yeah, I think
Because
so.
it looks
Yes.
like it might be -4 and 9.
9. Oh, okay.
See?
Yeah,
So
that's
yeah, so you have to
put
read
in the
it
numbers
really
wrong.
carefully, correct? You have to read it really carefully there. So let's see. So let's try. Let me try this and see what happens. So so it looks like I'm thinking where is my bracket here though? Wow, they really make me look for that. So on the keyboard, maybe that's easier to find for you guys, but it looks like it there is starting to increase at -4, okay?
Okay.
And then that's continuing to 9.
Yes, I think so. Yep.
And all right, so how do I check this now? Is there a submit answer here? So I'm only going to enter just the increasing part and see if maybe we got that. Yeah, so you got that one right. So I think it's just a matter of I think it's just a matter there of looking. I think it's just a matter there of looking kind of carefully, Mohammed, at
I see
graph,
what
right?
you mean. Yes.
Okay. Yeah. All right. And then entering that in interval notation. It is a little bit harder to enter where it's decreasing, right? You are going to have to rely on the palette, right? Because for decreasing, for instance, it's going to be decreasing from say 9 here, starting on the x-axis, and then it continues all the way along the x-axis. Doesn't stop at 15, so it would continue all the way out to infinity. So then you have to use your your little symbol palette here, which normally shows up on the left here. I can't see it on I can't see it right now, but that maybe I have to click it. Yeah, there's the symbol palette. I don't know if you guys can see it, where you can get the infinity symbol. So you know how to enter that, right?
Yeah.
Okay. All right. So it would be decreasing here from -infinity to -4, and then union from 9 to infinity. The union is that little stylized U. Is that, you understand that, how to enter that?
Yep, I got that. Yep.
Okay, all right. And then this one is even harder to read. Okay. Number 16 is even worse, right? Okay. Because you have got lots of turning points here. Remember, a turning point is where it's going to switch from increasing to decreasing or vice versa. So you've got 1, 2, 3 turning points here. So your answers here for increasing, decreasing are going to be kind of complicated. Okay. Because you've got several places where it's increasing and several places where it's decreasing. And remember, you want to combine those with the union symbol on the math palette over here. Well, on the math palette there on the left-hand side of, on the right-hand side of the screen, I mean. Okay. All right. Other questions like that? From the homework, especially this one, since I've got it open. So,
No other questions.
okay. So
Can we do
anyone
the
else?
last question?
What?
Can you go over
Can we do
concavity?
the last question? This one?
The last one?
Yeah,
Yeah.
concavity.
Oh, okay. Yeah. So that one's a little bit ahead of. We haven't talked about concavity yet. All right. So, but we're just getting ready to talk about that. Okay. So, so this will be more clear when we finish here in just a few minutes talking about concavity. All right. So yeah, because I haven't got to that. We stopped at increasing and decreasing last time. Let's see, where is this one increasing? Notice here they did not write the answer in interval notation. They wrote it just as an inequality, but this thing is increasing what? From negative infinity up to b, right? So that means it's increasing for all x values less than b. Actually, we would say less than or equal to b, but they've got less than b, right? And then it's going to be decreasing for all x values greater than b, okay? All right, now you may be wondering, what is the c in there for then? What does that have to do with increasing and decreasing? And the answer is, it doesn't, that value c along the x-axis doesn't have anything to do with increasing or decreasing, but it does have something to do with concavity, which is what we're getting ready to talk about coming up, okay? All right, so as soon as we finish our discussion of concavity, then this one will be much easier to answer. I also see someone who says they don't understand number 7. Melissa? Okay, let me let's scroll up to that one and see what
Yes.
that one's about.
Yes, sir. It's just the
Oh yeah, I knew
cosine.
this one. Okay, I knew I was going to get y'all with this one. Okay, so because this involves some trig, right? Okay, and so you're going to have to remember here a little bit of trig. In this problem, we're doing a function composition. Okay, we just looked at a very short 1 or 2 examples of this last time. Remember, in function composition, right, you're using the output from one function as input to another function. So here we're using the output from the function g, in this case, the output that matches the input 2 for the function g, and then we're feeding that into the function f. So we're going to have to evaluate first the function g at the input 2, see what output we get, what y value we get, and then we're going to have to use that as input to the function f, okay? So you're going to be evaluating a function twice, first the function g and then the function f. But what makes that a little bit, and that's the case in all of these, parts here to this problem. But what makes this maybe a little bit hard for you is that these are trigonometric. Well, this one is not, but f is a trigonometric function, right? Okay, so that's a little bit that this forces you to remember a little bit about trig. Okay, all right, so Melissa, let's try this without me writing it down. Let's just talk through it. So first, let's evaluate g of 2. So what are you going to get when you plug a 2 into the function g? So you're going to plug 2, there's the 2, you're going to plug that in for x, right? So what do you get from that? When you plug 2 in for x, what result do you get? What?
2 pi.
Yeah, you get 2 pi. Yeah, sure, you get 2 pi, right? Okay, so g of 2 is 2 pi. And then you have to take the 2 pi and plug that in for x in the function f. So what you end up with here is f of 2 pi, I'm sorry, cosine of 2 pi, all right? So you have to remember what is cosine of 2 pi. Do you remember what cosine of 2 pi is? Shall I draw that for us?
0. I think it's 0, is it not?
Yeah, well, is it 0? You got to
It's
remember
1.
how we have to remember how cosine
Negative
works,
1.
right? So we have f of g of 2, but you told me, well, g of 2 is easy. That's just pi times 2. So that's 2 pi. And so now we have f of 2 pi, but that's cosine of 2 pi. And then you have to recall what cosine of 2 pi is first. What does 2 pi look like when you draw that angle? That's 1 revolution, right? So if you draw that 2 pi, right, you end up just with 1 revolution, and you end up back here along the positive side of the x-axis, right? That's the same as 0. So cosine of 2 pi would be the same as cosine of 0. And you just have to remember what cosine, right? Because when you open this angle, you're back along the x-axis. That's the same as the angle 0, right? So you have to remember what cosine of 0 is. Did you tell me, Melissa, and I wasn't paying attention?
No, I thought it was -1.
It's close. It's just 1. It's positive. Yeah. Cosine of 0 is 1. So cosine of 2 pi is same as cosine of 0, but that's 1. Remember, the way cosine works is it starts at 1 at 0, and then and then as you open up your angle, it goes it starts at 1, then it goes down to 0, then it comes back to -1, then it goes down to 0. I'm sorry, is that the way it works, right? Yeah, it goes down to 0 again, and then it comes back up to 1. So cosine of 2 pi is 1, same as cosine of 0.
Thank you, sir.
Yeah, so that's going to be the same thing in all of these. That's going to be the same thing in all of these. Going to be the same thing in all of these problems. Let's see, like for instance, the next one, f of g of 1/2. All right, so f of g of 1/2. All right, so well, g of 1/2, that is, gotta stop touching my screen. So this is f of pi times 1/2, right? Because isn't that what g was? It was pi times whatever was input to g. So you have f of pi over 2. But now we have to remember, what's cosine of pi over 2? Well, that's pretty easy, right? Here's pi over 2. This is pi over 2. But remember, cosine starts at 1. And then when you go up to pi over 2, it goes down to 0. So cosine of pi over 2 is 0. Yeah, we are going to have to, we will occasionally here in the class be using trig functions. So we do calculus with trig functions, just like we do with algebraic functions, like polynomial functions. So we are going to have to remember a little bit of our facts from trig. We'll get a chance to review those a little bit before we really heavily use trig functions in calculus. You don't have to review a lot, so you don't have to remember a lot of the details from trigonometry, but some things like cosine of pi over 2, simple things like that, or cosine of 0, those sorts of things you'll have to recall. All right, so but we'll have a chance to recall that before we get heavily into that. Okay, other questions then about the other questions and about the homework in particular? So these are all gonna
Professor,
work
did you,
the same way. Go ahead, Saad.
did you already demonstrate question number 4?
Question number 4. No, I did not. So let's go up. Oh, same thing, right? Okay. So
Okay, yeah, never mind. Then I can do it. Since you showed the previous question, I would be able to do this.
yeah. So again, this is just remembering. This is just remembering cosine of certain special functions, right? I mean, special angles, right? So I have you may have seen in other classes little charts of special angles to help you remember sine and cosine and tangent of special angles. I'll post another chart like that one that will help remind you of sine and cosine and tangent of special angles. Of course, your calculator may help you too here. Make sure you're in radian mode, however, right? Make sure you're in radian mode with your calculator, because these angles are given as radians, not in degrees. Okay. All right. So other things there? Okay. So I promised just a quick poll question. This one's going to be so easy now. So let me switch back to the notes here, and then
actually, I have one last question that I'm stuck on. It was
yeah,
number 7, letter D.
Number 7, letter D. All right, so Calvin, let's see, number 7, D, this one.
Yes, sir.
All right, so here we flip the order, right? So first you're calculating f of pi over 4, and then once you calculate that, you're using that as input to, you're going to use that as input to G, right? So I'm moving the screen here, so I probably can't see me anymore. So let's see, here we have G of F of pi over 4. But so that's G of, remember, F is cosine. So you have the cosine of pi over 4. Calculate that first and then plug that into G. So, is it Calvin? Calvin, do you remember what cosine of pi over 4 is? So that's a special angle again. So can you recall from your, enough of your trig, do you remember cosine of pi over 4?
I believe, give me one moment because I have it written down somewhere.
Okay, well, I'll tell you. It's cosine of pi over 4 is square root of 2 over 2. So pi over 4 is 45 degrees. Cosine of that is square root of 2 over 2. So is sine of that, by the way. Sine of pi over 4 is also square root of 2 over 2, right? So that's what cosine of pi over 4 is. Now you're calculating G of that. But G was easy, right? Because all G did was take the input, the x, right, and multiply it by pi. So here you just have pi times square root of 2 over 2. So there's your answer. It's pi times the square root of 2 divided by 2. And you can leave that in that form. That's that simplified form. It didn't ask for a decimal approximation, did it? So you don't have to write down a decimal approximation for what pi times the square root of 2 over 2 is. Who knows what that is, okay? I'm thinking that is a little bit over 2. But anyway, you don't have to get a decimal approximation. You can just leave it in this form. Does that make sense?
Thank you very much. Yeah. Yes.
Okay. All right. So again, yeah, those sines and cosines of those special angles. That's something that again will be coming up in the class, and so at some point we need a chance to review that. Right. Here's a little bit of a chance to review that, but that will be coming up again in the class. Okay. Let's see. So let me give you all here the our first poll question. So there we have a nice wiggly graph, right? So that is also the graph of a polynomial. I didn't write the formula for you. That's red graph right here. Is the graph of a polynomial. I think it is 3rd degree. So it's got, that means it has an x cubed term in it. So it's got x cubed, it's got x squared. I think it's got x in it, but I didn't write down the formula. And what I'm interested in knowing here is where is this decreasing? Where is it decreasing? So look at that and write down for me where it's decreasing. That's going to be the substance of the poll question, but I want to show you the graph first so you can write that down, okay? So everyone can see that, right? That red graph. So just where is that decreasing? So look at that as closely as you can, see if you can figure that out, and then I'll show you the poll, because the poll is going to block the picture, I think. So write that down first. Decreasing where? I'll give you all a few seconds there to write that down. We don't want to take too long because this was just meant to be a warm up, but we've already kind of warmed up on that. So, all right. So y'all write that down where it's decreasing. Okay. So let me get the right poll here, and I think it's this one. Okay. So yeah, that's the right one. All right. So now y'all can answer. Maybe if I move this to the side, y'all can still see everything. Yeah. Okay. So where is that decreasing? So whatever you wrote down before, just choose that one. Choose that one in the list if you see it. If you don't see it, I guess you can answer none of these. Yeah, decreasing. Andres, decreasing. Okay, so let's go ahead and enter answer. So if you're struggling with it, just pick something, okay? Go with your gut here, and answer something. Okay, I'm going to end the polling. So I got a lot of people who didn't answer. So this is a pretty straightforward question. So either you're not paying attention, or maybe you can't answer for some reason on your device. All right, but this would be a test question that really should be kind of a gimme question. So I'm going to end the polling here, and then I'll share the results. And indeed, for most people, this was easy. Okay, so I think we had 18 answers and 15 of y'all got it right. Yeah, this is decreasing from -3 to 2. Remember, you're going to answer in terms of the x-axis always, right? Okay, so if you're moving left to right along this curve, right, as you're moving left to right along this curve, right, where are you going down, right? Where are the y coordinates going down? And that starts at the x-axis right here, correct? At this turning point. Remember, this is called a turning point. All right, that point is called a turning point, and that behavior continues as we move left to right until we get right here on the x-axis. So this turning point occurs at -3. This is -3 on the x-axis, and then this turning point occurs at 2 on the x-axis. So indeed, it's decreasing from -3 to 2. I tried to fool y'all by also putting that it was decreasing from 4.5. This is 4.5 on the y-axis. I put it was decreasing from 4.5 to -2.5. This is -2.5 on the y-axis. Sometimes students give their answers in terms of the y coordinates. So some students would say, oh, this is decreasing from 4.5 to -2.5. But that's going backwards. You always want to give your answers in terms of intervals along the x-axis, right? Okay, so yeah, most of y'all got that right. So I think the class is really understanding that. I want to point out now, again, I mentioned this point here, if I can get this to right, this point here and this point here, these are called turning points, because that's where the direction of the function is changing, right? That's where the direction is changing from increasing to decreasing and then back to increasing. So where function direction changes, those points are called turning points. Make sure a turning point has to be where the direction changes from increasing to decreasing or vice versa. So a turning point is just not where you have a bend in the graph. You can have bends in the graphs that are not turning points. Turning point is where it switches from increasing to decreasing or decreasing to increasing. Must switch direction at a turning point. So this is an example of a turning point. Here also is an example of a turning point. Now, of course, this point happens to be -3 and 4.5. And this point is 2 and -2.5. The y coordinates of the turning points, those have special names. So this y coordinate, not the x coordinate of the turning point, but the y coordinate of the turning point, that is called either a local maximum or a local minimum. This 4.5 is an example of a local maximum, okay? Because notice that close to this point, that is where the y coordinate is maximum, right? Around this point, the y coordinate is maximum at 4.5, okay? And this y coordinate at this second turning point, this is called a local minimum, because close to this point, -2.5 is the smallest y value. Close to this point, -2.5 is the smallest y value. The reason I have to say close to this point is that if you look far to the left here, eventually your y coordinates are going to get smaller than -2.5. Over here on the far left, this graph is falling off to negative infinity. So ultimately, on the left, the y-coordinates will be less than minus 2.5, but close to this point, minus 2.5 is the smallest y-coordinate, and close to this point, 4.5 is the maximum y-coordinate, right? It's the largest y-coordinate. Eventually, over on the far right, the graph will keep climbing, and you'll have y-coordinates that are bigger than 4.5. But close to this point, 4.5 is the biggest output, is the biggest y coordinate, right? So that's why this is called a local maximum. Local to this point, this is the maximum y coordinate, and why this is called a local minimum. Local to this point, minus 2.5 is the minimum a y coordinate. Okay, so keep this terminology in mind, right? These are turning points, and the y coordinates of turning points are either local maxima or they're local minima. Forgot what I was going to say. Now, yeah, sometimes we confuse our terminology a little bit. So you may sometimes call the entire point here a local maximum. Technically, that's not correct, okay? The point is a turning point. The y-coordinate is the local maximum. But sometimes we get a little bit sloppy with our terminology, and we may refer to that point as a local maximum. Same thing for this, this turning point on the bottom. That is a turning point. The y-coordinate is the local minimum, but sometimes we will refer to the point itself as the local minimum. So be aware of that sometimes when we're talking about turning points and local maximums and local minimums. Okay, which we will be talking about a lot. Let me close the polling here now, and I'm going to change the share back to the notes so that we're only looking at the notes here. So we can finish up with this set of notes. All right, so we sort of finished talking about increasing and decreasing. That's called function direction. So that's one of the important properties, again, that we consider in functions that we consider in calculus. All right, the second important property that we're going to consider here is what is called function curvature. So functions have direction, right? Functions can be going up and they can be going down. They can be increasing or decreasing. But functions also, they're graphs, right? Also have curvature, right? They're not, most of the graphs that we look at here are not straight lines, right? They bend a little. Okay, and the amount of this curvature is something that we're going to be interested in calculus. All right, so a second important property of functions, in addition to a function going up or down, is how a function is curved, how a function is bent. All right, now let me describe here how we're going to talk about a function curvature. Okay, and there's really just two basic, really kind of three basic cases. I didn't write down the third one though, because it's kind of obvious. All right, so again, suppose you're looking at an interval in the domain of a function, so an interval along the x-axis, right? So above that interval, if the graph appears to be a portion of an arc opening upward, so a portion of an arc, it doesn't have to be an entire arc, but or just a portion of an arc opening upward, we say that the graph is concave up. It's curved concave up. So when I say arc opening upward, I mean something like this. All right, see, that's kind of an arc, right? But it's opening upward. So if you have this curvature in your graph, that's called concave up. All right. If you have the opposite case, where the graph appears to be a portion of an arc opening down like this, okay, that is concave down. All right, so a bowl-shaped is a concave up, kind of a hill-shaped is concave down. Those are the basic ways we talk about the curvature of a graph. Now, of course, you don't have to have a graph curved up or down. You could have a straight line, okay? That has no curvature, right? So that doesn't have any concavity, all right? So that's the third case that I kind of left out. That's kind of the boring case. So you can have concave up, you can have concave down, bent up, bent down, or of course you can have no curvature at all, which is a straight line, all right? Okay, now, well, let's just, that idea seems really easy, right? Let's explore it here with an example. So I have a very simple example here. This one here, this blue graph on the right. So that looks like just another polynomial function, right? Okay, and so let's write where this is concave up and where it's concave down, and it's not a straight line anywhere. So it always has some sort of concavity, all right, on the graph. Okay, so look at this. So let's go from left to right again. Along the x-axis, just like we would if we were thinking about where a function is increasing or decreasing, right? So what about this portion over here on the left? What is the concavity for that piece? So see, that's bent down, right? So how do you describe that? Someone
Just concave down.
That's concave down, right? So this piece on the left is concave down. All right, so that's fairly clear, right? It's going to be concave down over on the left. Now, what we have to figure out is exactly where it's concave down. All right, so that apparently starts at minus infinity. I can't see all the way to the left here, right? But you know, you're thinking this graph is going to continue, right, to the left. So that concave down behavior starts on all the way at minus infinity. Now, where does it appear to stop? This is the tricky part, okay, of trying to figure out where it stops at. And I'm guessing, just to make it easy on myself, I'm thinking right there, right at that point, which is at 2 on the x-axis, okay? See, it's bent down until you get about to 2 on the x-axis. And notice what's happening here on the right, it's concave up because this is an arc that's bent upward, right? Okay, this is an arc that's opening upward. So it's concave down from minus infinity to 2. And then it's on the right, it's just the opposite. It's concave up. So we would say it's concave up from 2 out to positive infinity. Now, it's sometimes very difficult to eyeball these places where a graph switches from concave up to concave down. And people's answers will vary sometimes a little bit when I ask this question. So you kind of have to be prepared there for a little bit of a disagreement here about where a graph switches from concave up to concave down. We're going to explore that in depth in calculus, however, and we'll learn how to answer that question more accurately. But visually, sometimes that's a little bit tricky. This point, however, where it switches from concave down, that's kind of like a turning point, except it's not the direction that's switching, it's the concavity that's switching. This point has a name. This is called an inflection point. I know y'all have heard that term because people use that term in the news all the time. They say some situation has reached an inflection point. Well, and they sometimes use that term in different ways. But in mathematics, inflection point means point on the graph where the concavity switches. Okay, so here it is on this in this particular picture. Is that kind of making sense? Well, let's try that again. All right, so let's see if we can discuss the concavity of this one. All right, so just where is it concave up and where is it concave down? Pretty easy, right? Okay, what's happening over here on the left? How is that graph shaped, or how is it curved there on the left? Which is that?
Concave down.
Yeah, that's concave down, right? Okay, so concave down initially, right? On the left-hand side. So concave down, and apparently that's from minus infinity up to, but where does that stop on the x-axis? It stops somewhere on the x-axis because right, this part is concave up, right? Okay, so you see it somewhere, it switched from concave up to concave down, and I guess that's right here. I've got that point drawn. So it must be right there at the y-intercept is where it switches, right? This part is bent down. This part, on the other hand, is bent up. So it's concave down from minus infinity to 0. And then opposite on the other side, right? This is concave up. Okay, from 0 to infinity. Is that sort of clear? Well, we'll see. Let's let y'all try one here. Okay, this is an applied example. Let me get my boxes out of the way. So let's read the story here. But the story is not really all that crucial to us at the moment. Let's see. This graph shows the the number of injuries. So, well, this is kind of depressing. The number of injuries resulting from car accidents. So this is in millions, okay? Because there's, lots of car accidents, lots of injuries from car accidents. And the X here, so the values along the Y-axis, this is numbers in millions. And then along the X-axis here, this is elapsed years after 2000. So it looks like this thing starts here at 23. So a little bit in the future, and then goes up to 32. That would be 2032, right? This is 2023 is where the graph starts at. Okay. Notice it doesn't go to infinity on the left and the right because we have the dots here. So those definitely cut off the graph. So the domain doesn't go to minus infinity on the left. It doesn't go to positive infinity on the right. Okay. All we want to know is where is it concave up and where is it concave down? So where is this graph concave up? Where is it concave down? By the way, notice it's always decreasing here. It's decreasing from 23 to 32, but we're not worried about decreasing. I want to know about the concavity. So where is it concave down and where is it concave up? And then where is the inflection point? So if it switches concavity, then it must have an inflection point where that change occurs. So what are the coordinates of the inflection point? You'll just have to estimate them from what you can see there. Okay. All right. So see if y'all can write that down. Where is it concave up? Where is it concave down? And then where's the inflection point? What are the coordinates for the inflection point? All right. So can everyone see that? All right. I'll give you all a couple of minutes there. Oh yeah, just a couple, so we can get through with this before we take a break. I'm gonna ask someone, so or a couple of people here, so make sure you've given it a try here, right? Concave down, concave up. If you can answer concave down, then you can answer concave up and vice versa. And then where does it look like the inflection point is? And probably answers are going to vary here a little bit because people are going to see this slightly different. So just take another minute. Again, you don't have to give your answers perfectly here. Okay. Then I'm going to ask someone, hopefully someone I haven't called on. I've been trying to keep track of this. So, but Been trying to keep track of this, but okay. All right. So let's see if we can just write something down here. Luis Ruiz, Mr. Ruiz, are you there? Can you hear me?
I think he's texting in the chat.
Oh, there you are. Oh, okay. All right, Luis. So, so can you can put it in the chat. I'll write it down for you. So, where do you see that as being concave up? Concave up. So where does it appear to be bent upward? Remember, give your answer in terms of the x-axis. So where is that curve bent upwards? Where would that start at and where would that end at? So you said concave up from 32 to infinity, okay? Well, so if it starts right there, if it starts being bent up at 32, then right there and goes to infinity, that can't be the case, right? Because the graph actually stops at 32. So the graph doesn't even extend out to infinity. All right, Lewis, okay? So you see that you can't start it being concave up at 32 because that's the end of the domain. The graph actually stops there at 32. Okay. Oh, all right. So around 28. Better guess there, right? Yeah. And this is the part that's a little bit tricky. See, this piece of the graph is definitely bent upwards, right? It's not a huge curvature, but it's definitely bent upwards, right? This piece is bent up. Now this piece, on the other hand, though, you can see is bent down, right? So that where it's bent up has to start somewhere. And I think you're right, Lewis. If you were going to eyeball it there, you might say right there at 28, right? Okay. Yeah, I think that's a good choice, right? Okay. And so it starts at 28 being bent upwards and then continues out to where, Lewis? Where does the graph stop at anyway? Yeah. So you would write your answer here for concave up as 28 to 32. Okay. And in this case, you have to stop at 32 and go instead of going to infinity. All right. So Lewis, where is it concave down? Going to be just the opposite. So where is it concave down? Where does it start being concave down? Where does the graph start anyway? Can you see what that number is? Kind of hard to read that, but can you guess what that is? Yeah, 23, right? So it starts being concave down at 23. And where does it quit being concave down? Well, that's where it starts being concave up. So where'd you say it started being concave up? At 28, right? So quits being concave down at 28. Ah, nice. Okay. So 28 to 32, a concave up, right? And 23 to 32 concave down. Good. So anybody have questions about that? So you may disagree a little bit where this point is. You may have it slightly a little bit further to the left or a little bit further to the right. Okay. But somewhere right around there is that inflection point where it switches from being concave down to being concave up. Right. So there is the inflection point. Let's see. What does it look like? The coordinates of that are 28. And what about the, oh boy, the Y coordinate's hard to read here, right? Maybe 1.1. I'm just eyeballing that. Looks like about 1.1 is the second coordinate for that inflection point. But there it is. There's the inflection point. Okay. All right, so there's the second big property we're going to be studying here in calculus. After direction, we're going to study curvature, right? Okay, and this is how we talk about curvature in terms of concavity, and where curvature changes, these important points are called inflection points, all right, where it switches from concave down to concave up or vice versa. So those are kind of similar to turning points, but where the function changes direction, inflection points where a function changes concavity. Now, there's one other major feature we're going to study here of functions in calculus, and so that's the third one we want to talk about. And but we're past 12:30 already, so let's take a break here until about 12:40. I've got 12:34, so let's take a break till about 12:30, and then we'll come back and talk about that last important property. Okay. All right. So I'm going to pause the recording there for a second. Okay, so the third big property that we're going to consider here about functions in calculus is what is called continuity. So the three properties are direction, right, increasing, decreasing, curvature, concave up, concave down, and then what's called continuity. And so let me explain to you what continuity is. So this is pretty easy to understand conceptually. A function is said to be continuous, again, over an interval or on an interval in its domain, okay? So we always discuss continuity in terms of an interval in the domain of the function. So it's said to be continuous if the graph is an unbroken curve, okay? So if you have an unbroken curve above a particular interval in the domain of the function, then the graph is said to be continuous for that interval. So here's just an abstract example of that. Here we've got a curve, and so notice that for this portion of the x-axis, this portion of the domain of this curve, right, starting at A and going over here to B on the x-axis, notice that you have an unbroken curve, right, along that or above or below that interval. So in that case, this function f, we would say it's continuous on or over the interval from A to B, okay? All right, so again, if for a particular interval in the domain of the function, particular interval along the x-axis, if the function graph is an unbroken curve, okay, then the function is said to be continuous. So just that simple. All right. So that seems like a very simple idea, but again, it plays a real key role in calculus. All right. So let's look at some easy examples here of this property continuity. All right. So what we're asking here is in this example 7 is it says determine which of the following functions is continuous on this interval, and this interval is this big interval, which is the whole x-axis. So all the way from minus infinity to positive infinity, okay? So all the way from the left, right, all the way over to the right is this function continuous. All right, so what about this one, this nice graph here of this function? Would we say that that's continuous? So again, continuous means it has to just be an unbroken curve. So is this graph in A going to be continuous from minus infinity to infinity?
No.
No, right, okay, because obviously, why not?
Because it's not all connected all the way through.
Right, it's not connected, right? It's got this big break in it here, right along the y-axis, right? Okay, so definitely not continuous. Okay, all right. So you can think of continuous as being a synonym for unbroken. All right, that's where that term continuous comes from. Okay, so yeah, definitely not continuous. Now that's from minus infinity to infinity. If you look at smaller parts of the domain, the function might be continuous. For instance, if you only looked from, say, 2 to 6. So if you only looked at that part of the domain, then the function would be continuous for that interval, right? Okay, because from 2 to 6, the curve is unbroken. But from minus infinity to infinity, it's not unbroken. So not continuous from minus infinity to infinity. So curves can be continuous in certain places, right, but not continuous in other places as well. What about B there? So again, the question is from minus infinity to infinity. So is this one continuous?
No.
No, for the same reason, right? You've got this asymptote here, right, along the x-axis that breaks the graph into two distinct pieces, right? Two disconnected pieces. You've got this piece on the left and the piece there on the right. So again, definitely not continuous from minus infinity to infinity. It might be continuous for certain segments of the domain, right? Okay, but not all the way from minus infinity to infinity. What about C here? Is that continuous?
No.
No. Yeah. Now that one comes pretty darn close to being continuous, right? Okay. Because it's just a straight line. The problem that makes this, the reason that this is not continuous, right, is this graph has this hole in it, okay? And that breaks the graph up again into two separate pieces, okay? So you've got this one number, looks like it's the number 2, right? You've got this one number that's missing here from the domain, correct? You've got a hole here in the graph at the number 2, and so that keeps it from being continuous from minus infinity to infinity. By the way, I didn't just make this. Graph up. This is actually the graph of this formula. Okay, so when you graph this formula, you will get this graph. It's just a straight line, but it's got one hole in it right here at right there at the number 2. Let me show you why that's the case. By the way, this is you can sort of explain this from the formula. Why there's a hole in the graph here at the number 2. Let me factor here the numerator and the denominator in this formula. So x squared plus 4x plus 4, that factors, if I can get my pen to write again, that's going to factor as x plus 2 times itself. That factors as x plus 2 times x plus 2. And the denominator also factors because you can factor out a 2. So you can write that as 2 times x plus 2, okay? Now, the reason you cannot, the reason you have a hole in the graph here at 2 is, notice if you try to plug 2 in for x into this form, no, I did this wrong. Yeah, that's not the right formula. Let me see. Let me fix that. Wasn't thinking carefully when I this down. All right, I gotta fix the signs. Okay, so this should be a minus here, and this should be a minus. Okay, now when you factor it, you get x minus 2 times x minus 2 in the numerator, and then the denominator you have 2 times x minus 2. Now, notice that if you try to plug 2 in for x in this formula, you're going to get 2 times 2 minus 2. So in the bottom, you would get 0, and you cannot divide by 0. No matter what the top is, you cannot divide by 0. So that's why the number 2 is left off of this graph. So you have a hole here in the graph at x equal 2 because you cannot plug a 2 in for x in the formula. However, if you ignore the number 2, then notice this formula reduces because you can divide out x minus 2 from the numerator and denominator, and you just get x minus 2 over 2. And when you graph x minus 2 over 2, you're going to get a straight line. Okay, I'm not sure if it's this straight line, by the way, but you just get a straight line. So so the graph looks like a straight line, except for it's missing the number 2 from the domain. Okay, so not continuous because of this hole in the graph here at the number 2. What about D? Is that continuous?
Yeah, it's
So you got this jagged looking graph. What?
Yeah, it's continuous.
Yes. Yeah, that's continuous, right? Because you don't have any breaks there in the graph. So this one is continuous from -infinity to infinity. By the way, is that point a turning point?
Yeah.
Yes.
Yes, that is a turning point because you're switching from increasing to decreasing at this point, okay? So that is a turning point. So we have a turning point that looks like at coordinates -3 and 1. So we have a turning point at -3 and 1. This would be a local maximum. The number 1 would be a local maximum. And this also is a turning point. So we have another turning point at, it looks like 1 and -2. And -2 would be a local minimum. This is a turning point because it's switching from decreasing to increasing. What about the concavity of this graph?
Concave down and then concave up.
Someone's saying something. Can you talk louder?
Yeah, I was trying to say it's concave down and then it's concave up.
Yeah, I fooled you there. Okay, all right. You're thinking this is this part is concave down, but notice that is not an arc. Okay, not an arc. What you have here are, because you have 3 straight line segments here, right? You don't have any concavity, so there is no concavity here. Does that make sense? Straight lines don't have any curvature. Okay, so no curvature here or here or here. To get concavity, you have to have something like this. Okay, the curvature has to be kind of smooth. All right, so this, even though here it's kind of, you're thinking of it as kind of being bent downwards, it's not, because these are line segments. All right, so no concavity. That one's kind of tricky. All right, in terms of the concavity. Let's see if I can erase my dots here. Okay, all right. So continuity, that's the other feature there. The third important feature there that we're going to look at in calculus. Okay, all right. So now we're going to switch our attention a little bit, and we're going to concentrate more fully on direction. Okay, so again, we're going to study direction, curvature, and continuity. Okay, so let's start first with direction. So I'm going to change notes here. And I'm going to change the screen share. Okay, so can you guys see that picture? That's the that is the graph of that's the daily graph of COVID cases in the U.S. Well, since the beginning of the pandemic up to very recently, I think. This goes up to the end of January. So that's the blue curve is sort of the this is sort of what we want to focus on here. All right, that's the that's sort of the curve that shows these COVID cases. And of course, you know, that's been sometimes that curve is increasing, right? And sometimes that curve is decreasing. So it's changed directions, right? It's changed directions a lot, okay? And fortunately, currently we're over here on the right-hand side of the curve, and the curve is currently decreasing, all right? So that's good news for all of us at the moment, all right? But you know, the curve again has increased and decreased a lot, right? So, you know, not entirely clear, right, what's going to happen going forward. So, you know, curves, right, they change direction a lot. And so, or they can change direction a lot. And so that makes direction, you know, sometimes a difficult subject to study. And one of the things that we're interested in direction is how to measure how fast a function is increasing or decreasing. Okay, so we want to be able to not only discuss the direction of a curve, whether it's going up or going down, but we're also interested frequently in how fast the curve is going up or how fast a curve is going down. Okay, in other words, how the curve is, how the y coordinates, right? How the output values from the curve are changing, right? As x is increasing. The reason I showed this graph is because that's exactly the sort of a problem that this graph is trying to get a handle on, right? Okay, because there were in the pandemic, there's been 3 distinct surges, okay, in cases. Of course, there was the surge at the beginning of the pandemic, right? Early in the last year, right? Okay, so there was that initial surge. And then there was another surge in the summer, okay, that affected some areas more than others, right? But in the middle of the summer, there was another surge in cases. And then, of course, there's been this awful surge here that started in the fall of last year, right? That's been the biggest surge of all. And in what this graph is trying to illustrate, right, is sort of how big, right, how rapidly those surges happened. All right, so or how rapidly the increase, how rapid the increase in those surges were. Notice the way that they tried to illustrate this is they kind of replaced part of the curve with a straight line. Okay, so they sort of laid a straight line here on this surge right at the beginning of the pandemic, and then this surge in the summer, right? And then this surge here in the fall to kind of illustrate, right, how steep or how rapid those surges were. Okay, and there's of course a good reason why they put a straight line here on the curve, and that's because straight lines are easy to understand their increase or their decrease, right? Okay, so that really gives us a helpful visual tool, right, for understanding these surges. I wanted to use this example as kind of to illustrate the beginning of these notes, okay? Because this is exactly the problem that we're going to be taking up in these notes, trying to measure how rapidly a curve is increasing or decreasing, all right? Or how slowly a curve is increasing or decreasing. And this graph kind of does a good job of that by putting these by laying these straight lines on the graph, so that it's easy to visualize how big this surge was compared to these other two, because straight lines are easy to understand. And in a sense, visually they're easy to understand, but also computationally they're easy to understand. And in effect, that's what transforming these curves into straight lines, and is in a way how we're going to be able to measure the direction of curve. Measure the direction of a curve, right? How rapidly it's increasing or decreasing. But I have to explain how we're going to do that. You have questions so far? Okay. All right. So that's just an illustration let's scroll back up here to the top of the, let's scroll back up here to the top of the notes. Okay, so there are kind of three ways that we're going to introduce here to measure change in function outputs, how rapidly functions outputs are changing. In other words, how rapidly a function's outputs are increasing or decreasing. All right, okay, and they're all kind of related. The first one is very simple. And then the third one that we're going to introduce here, this is the one that is really the one we're going to focus on. Okay, so kind of the key question here is, how do we measure change in outputs in a function, right? And so how do we measure the direction increasing or decreasing of a function? All right. All right. So our first simple measure is what we're going to call just net change. Okay. Or if you leave the, sometimes you'll see the net leaved off and you'll just see change. All right. Okay. So now, for us to compute this properly, I've got to make sure we set this up right, okay? So suppose you have a couple of input values, x of 1 and x of 2. So these are just two different input values, all right, okay? So just think of these as two numbers along the x-axis, right? And of course, you've got some function, correct, right? And we're going to assume here that x of 1 is less than x of 2. So this is a smaller x value, this is a larger x value. All right, then we just say that the net change in the function, by that we mean the net change in the function outputs, okay? All right, the net change in the function outputs from x1, the initial x value, to the terminal x value from x of 1, some x of 2, that is just calculated by taking the change in the output values from x of 1 to sub x of 2. So you would be computing f of x2 and subtracting off f of x1. All right. So the y value that matches x2, subtract off that the y value that matches x1. That's called the net change in f from x1 to x2. We're going to denote that so that we don't have to always write that out in words. We're going to frequently denote that by putting, this is the Greek letter delta, remember, in front of the name of the function. You can also put the delta in front of y as well, okay, if you don't want to use the name of the function, right? So that is just called net change. See, that's a very simple idea, right? You're just computing the difference in the outputs from x1 to x2, whatever that difference is, that's called the change. Now, sometimes, you know, that's a pretty simple idea. Sometimes now we, instead of dealing with net change, we like to convert that to a percentage, okay? So to convert that to a percentage value, all right, so if you want to compute what's called the percent change from x1 to x2, you just take the net change and divide that by f of x1, and then convert that to a percentage. So notice you take net change. This is the formula for net change, right? You divide that by f of x1, the output value that matches the input x1, and then multiply by 100% to convert this to a percentage, okay? So that's called percent change. Again, just another way of computing change. Now, the third way, and the one that's really more interest to us, and the one that we're actually already familiar with, is what's called the average rate of change. Notice its formula is very similar to the formula for net change and percent change. Okay, so the average rate of change from x1 to x2. Okay, you just calculate the change. All right, this is the formula for change. And then you divide it by the x of 2 minus x of 1, all right? the difference in the X values. Here's the way I'm going to denote this notationally. I'm going to write delta F over delta X. That is called average rate of change. All right, those are just three formulas. So let's put them into an actual problem, okay? And so let's calculate net change and percent change and average rate of change. But again, these three things are all just ways of measuring, sort of measuring the direction of a function, okay? How fast a function is increasing, how fast a function is decreasing. All right, so take a really simple example. All right, so the following function, which I have written here as a formula, okay, what this gives is the typical yearly earnings. So this is measured in thousands of dollars. This is for women with a high school GPA of X. All right, so what we're doing in this formula is we're predicting the typical, this is typical, okay, earnings for this is for a woman who has graduated from high school, okay, with a particular GPA. Notice this is a nice simple formula, and that's a linear formula, right? Okay, so when you make a graph of this formula, you're going to get a, when you make a graph of this formula, you're going to get a straight line. Okay, there is the graph of that formula. So, you know, this has a slope of 7.6, right? So the slope is positive. So, of course, the line is increasing from left to right, correct? The Y values are going up from left to right. Of course, that makes perfect sense, right? Because, it's a good thing it makes sense, because that tells us, right, as the GPA is going up, right? Then the typical earnings are also going up as well, okay? So, and that's what we would hope for, right? If we're working harder in high school to earn higher grades, right, we would hope that our earnings would go up. Keep in mind, this is just for high school graduates, right? So this is not for college graduates. So whether a person has gone to college or not taken into account in this example. All right, first let's answer the first question there. So what is the net change from X equal 1 to X equal 3? And then we want to just interpret that. So explain what that number, we just want to explain what that number means. All right. So again, the way I'm going to denote that net change is I'm going to put a delta, right? And then you can either put the name of the function there, which in this case is F, or if you want to, you can put a delta with a Y, okay? All right. So, all right. So what's the formula for net change? I've already scrolled past that, but it's so easy there. It's just going to be take your second X value, plug that into your function, and then take your first X value, plug that into the function, and then take the difference of those two outputs, right? Okay. So if you want to kind of say this in words, it's the you know, it's the earnings for typical earnings for someone with a high school GPA of 3 minus the typical earnings for someone, a woman with a high school GPA of 1, right? Okay. Let's see what these two values are. Okay. So so it's going to be F of 3 minus F of 3 there minus F of 1. All right, let's see. Can we do that? Can we do that arithmetic now? So what am I going to get when I plug 3 into my formula? So in other words, what's the typical earnings for someone, a woman who had a high school GPA of 3? Let's see. So it's going to be 3 times 7.6 and then plus 5.4. Well, let's write that down. So 7.6 times 3 plus 5.4, right? And while I'm talking, can someone do that arithmetic for me? All right, and then what's F of 1 going to be? Well, just plug 1 into the formula, right? So you get 7.6 times 1 plus 5.4 again. So let's see, what were these typical earnings? What's the 7.6?
28.2 minus
28.2, and then we're going to subtract off. Of course, it's going to be much lower, right? So what is this, 13?
That's right.
So we get there, wow, it's pretty big, right? 15.2. All right, so there is that net change. So if you want, I don't want to draw a picture of this. So if you want to draw a picture of this, right? Okay. There is, there's one. Y'all can't see that very well, but I can see it. There's 1 on the x-axis. There's 3 on the x-axis, right? Okay. And all we were doing was just calculating what's this difference, right, in these y coordinates from 1 to from 1 there to 3, and that turned out to be 15.2. How would we interpret that in words? So what is that telling us? So if you were going to explain to someone what that 15.2 means, can you think of a way of explaining what that number means? So it's positive. So something has, what's that telling us? Something has gone up or gone down?
The GPA increased.
Well, the GPA increased. That's right. Okay. The GPA increased from what? Saad? Because we said right there. So the GPA increased from what? Saad, can you answer that? The GPA increased from?
Is it 5.4?
What now?
Professor, can you hear me?
Wait, okay, I can't hear what you're saying. What are you saying there?
Can you hear me now?
Yeah, I can hear you.
I was saying, is it 5.4?
5.4. Well, you said the GPA increased. That's correct, right? So the GPA increased from what? Because there it's written out in the problem, right? So the GPA increased from what?
My answer.
Well, there it is. The GPA started at 1.
We're looking at the net change from 1 to 3.
Right. There's the net change from 1 to 3 is 15.2. Right. Okay. So the net change from 1 to 3 is 15.2. But I'm just trying to, in the context of the problem, what is that 15.2 telling me? So what does that mean? What does that mean to me?
That's how much it changed.
How much, when you say it, what is
GPA?
it? No, not the GPA, because the GPA went from 1 to 3, correct? So how much did the GPA? How much did the GPA change by?
Yearly earnings.
The yearly earnings, right? Okay, so you're right. The yearly earnings increased by 15.2. Okay, well, all right. So let me write down what you said there. So you said, let me write that down. You said the yearly earnings. Increased, or let's just say increased, just to keep it in the present tense. The yearly earnings increased by 15.2. So that means how much money is that, Saad? That's not $15.2. That's what?
We were looking at 1,000. So
1,000. Yeah, so it was 15.2 thousand, right? Okay.
Yeah.
So that's 15,200, I guess. All right. So you're saying that's your explanation. The yearly earnings increased by 15,200. Okay, that's almost correct. All right, but you're leaving off an important point. the yearly earnings increase by 15,200 when what changes?
When the GPA increased from 1 to 3.
Right. Yeah. You have to put that in, right? Okay. When the GPA increases from 1 to 3. Okay. Different changes in the GPA will lead to different amounts here. Correct. Right. So this is the increase when GPA increases from 1 to 3. Right. If I can squeeze that in, when GPA increases from 1 to 3. Yeah, there's the interpretation. Okay, that's correct interpretation. By the way, if the GPA increased from 0 to 3, right, this number would be different, right? Or if the GPA increased from 2 to 4, maybe this number would be different, right? Okay, so this is the change when the GPA increases from when the GPA increases from 1 to 3. Okay. So that second statement is really important there in the that second statement there is really important in the interpretation. All right, now let me convert this to a percentage and also, because sometimes we like to see numbers measured instead of as absolute amount, we like to see them measured as percentages. All right, so for a percent change, by the way, which we're going to denote this way, so we'll put the delta F again, and then we'll just put a percent sign after that, okay? So the formula for that is you take the net change, okay? You take the net change, so remember, that's my symbol for net change. You divide that by the output, the first output, so that would be F of X1, and then you convert that to a percentage. Okay, all right, so let's see if we can fill in these, let's see if we can fill in these values. We know what the net change was, right? What was the net change? That was 15.2, right? So notice net change is part of the percent change formula. So you have 15.2. What was F of X1? So what were the earnings? There's your X1 value, right? That was your first GPA value. What were the earnings for someone with a GPA of 1? Do you remember what that was? It's right there. We calculated it. So that was 13. So you divide here by 13 and then multiply by 100% to convert this to a percentage. Can y'all do that arithmetic for me? What's 15.2 divided by 13 and then turn that into a percentage by multiplying by 100%? I think I can do that on my calculator. So 15.2 divided by 13, I get this. It's about, I'm rounding off a little bit, about 117%. You get a really big percentage there, 117%. How do you interpret that? So what does that tell us? You can kind of use this as your example.
So the yearly earning increased by 117% when the GPA come from 1 to 3.
Yeah, perfect. Right. So use this. I'm not going to write that in there, but use this just exactly the same interpretation. Okay. So the yearly earnings increased by, instead of putting a dollar amount here, you would just insert the percentage. Okay. So yearly earnings increased by 117% as the GPA increases from 1 to 3. Oh, that's really good. 117%. That means it's doubled, right? Okay. More than doubled. 100% increase would be doubled. So as the GPA goes from 1 to 3, the average earnings more than double. Okay, right? Okay, in that case.
Sorry, in that question, where did you get 13 from?
That is in the formula. That's F of X1. So that would be F of your starting X value. Our starting X value was 1.
Okay.
And when you plug 1 into the formula, I already knew what that was because we calculated that a moment ago. That was 13.
Okay.
Sorry, I skipped that, okay?
No, you're
There's f of 1. F of 1 is 13. So I went through that kind of fast.
It's okay.
So that's good to know. As the GPA goes from 1 to 3, right, yearly earnings would go up by 117%. Now, here's the other way of measuring change, though, that we're going to be mostly concerned with. Okay, notice that in these two previous examples, we saw that the earnings went up by you know, a lot, 15,200 or 170%. But that was when the X changed by 2. Okay. But sometimes you would like to know, well, you know, what's happening on average to the earnings when X goes up by 1, right? So on average, every time you increase your GPA by 1, how much do the earnings go up? See, here we increase the GPA by 2, but we might also like to know, well, how much on average are we increasing the GPA as the GPA goes up by 1? That's what average rate of change will compute for us. Okay. All right. Now, again, that formula, we're going to denote that by that value. We're going to denote that by delta F over delta X. That's going to be our notation for average rate of change. Or you can write delta Y divided by delta X. Okay. So the formula for that is that's a net change, because delta F means net change, divided by the delta X means change in X. So that would be X2 minus X1. Again, how do you calculate net change there? Remember, that's F of X2 minus F of X1. And another way of writing F of X2 is Y sub 2, if you don't want to write F of X2. So all of these are just different ways of writing down that's so-called average rate of change formula. The reason I wrote it down in, oops, I'm out of time. The reason I wrote it down in all these different ways, I'm sorry I ran over. What does this look like? What formula is that? That's familiar to you already.
Slope.
That's the slope. Yeah. So average rate of change is really just slope. Okay. We've already done slope. By the way, what's the slope of this line? What's the slope of that line?
7.6.
7.6. So I don't have to do all the calculations here because I know this is really just the slope formula, and I already know what the slope of this line is. It's 7.6. Okay. And we even know how to interpret that value. So every time the GPA goes up by 1, the salary is going to go up by 7,600. Okay. So average rate of change is really just slope of a line. And we already know lots about slope of a line. Okay. All right. Well, let's quit there. Okay. Those are the 3 ways we're going to measure change. And that's a way of helping us understand the direction or measure the direction of a function. Okay. All right. So I'm way out of time. So I'm going to stop there. Sorry about running over. You'll have to caution me when I'm getting too close. Okay. So I'm going to stop the recording.